Okay, well, welcome to this SE5014 Chemical Science revision session. This is for the inorganic component of the 5014 course, and what I'm going to try and throughout this session is to answer the questions that I pose at the very end of each lecture. So throughout this lecture series, you will note that at the very end of each lecture there are a series of questions, and I don't have the time here to go through every single question. So what I've attempted to do is try and answer some of the trickier questions, some of those slightly more complicated questions from the lecture series, and I've avoided answering the questions that I would consider to be more kind of comprehension type tasks. So there were some questions on graphene and the structure of various compounds that form in inorganic chemistry. These are things that can be very quickly picked out of the lecture slides and are there for your own practice. So what I've tried to do is answer possibly some of the more mathematical questions, some of the more problem-solving questions that have been associated with each lecture. And I will go through the answers to these questions, go through the solutions to the problems, and again, I'm not going to reintroduce all of the topics here. If you would like a more detailed description of each individual section, then please look back over the appropriate lecture slide. So we'll start with the very first question then. Question 1 from lecture 1, and a couple of you have asked for answers for these questions because you found them tricky. Account for the fact that lithium fluoride and cesium iodide have low solubility in water, whereas lithium iodide and cesium fluoride are very soluble. And you are given the element along with its ionic radius. So you know straight away, just from looking at that question, that it's related to the size of the ions present in the salt. So we are looking at group 1 metal salts here. So the first question that we want to answer is, well, what happens when we solubilize or we dissolve a metal salt in water? Well, we're taking something that exists in the solid state and consists of an ionic solid, the cation and an anion, each with a defined radius. And we are dissolving that in water. We're splitting that up into its constituent ions in aqueous solution. So we're breaking up the actual lattice. And two things are happening when we dissolve a metal salt in water. Number one is that we know we've got to break up the lattice. We are going from the solid state to a salt dissolved in aqueous solution. So we know that we've got to break bonds. That takes energy. And we're also taking those ions and we're solvating them. So we're surrounding them with a shell of water molecules. Now that's a nice pictorial representation of what we're chemists, and we want to be able to describe that in much more detail. And we can think about the energetic processes that are ongoing here by considering the Gibbs energy of solvation. Taking a metal salt, and I represent that here as Mx in the solid state, and converting that into its aqueous ions M plus and X minus in aqueous solution. Of course, there is an energy change associated with that process, and the easiest way to look at it is through that Gibbs energy change of solvation. Now again, as chemists, we probably want to go into a little bit more detail, and we can split that solvation process up into a couple of different energetic steps. The first is to consider the change in Gibbs lattice energy that is associated with dissociating that ionic solid into its gaseous ions. We can think of that very simply as the lattice energy. So here we're going to take the Mx solid and we're going to dissociate it into its two ions in the gaseous state. And of course, that takes energy. We need to put energy into the system in order to break up the lattice. Once we've got those ions in the gaseous state, then we want to convert those gaseous ions into their hydrated counterparts. And so we need to take into account the Gibbs energy of hydration for both of the ions here. So the Gibbs energy of hydration for the cation and the Gibbs energy of hydration for the anion. And if you look at the energy flow throughout that system, then we can very easily calculate the overall Gibbs energy of solvation by summing all of the other elements around the Gibbs energy cycle there. So in order to calculate the Gibbs energy of solvation, we need to take the Gibbs lattice energy, add that to the Gibbs energy of hydration for the cation, and add that to the Gibbs energy of hydration for the anion. And that gives us a nice, easy way to predict whether or not something is soluble in water, because we know that if the Gibbs energy of solvation is negative, then the compound will be soluble in water, i.e. the solubilization of that salt in water is energetically favourable or spontaneous. So to look at that equation in a little bit more detail, the overall Gibbs energy of solvation here, which is the thing we're trying to work out to predict whether or not a salt will be soluble in aqueous solution, has a very small magnitude, whether that be negative or positive. And if it has a very small magnitude, then what it tells you is, or what it implies, is that very, very small changes in the other parameters within that equation are going to have a very big impact on the solubility of a salt. And the Gibbs lattice energy and the Gibbs energy of hydration for both the anion and the cation are very, very sensitive to the radius of the ions that make up that salt. So if we change the radius of the ions, we change the parameters that make up that equation, and we have a big impact on the Gibbs energy of solvation. Now that Gibbs energy of that Gibbs lattice energy tends to have a high magnitude. We're talking about ionic solids here that are very attracted to one another, and in this context it has a positive value, because remember, when we're dissolving a solid in solution, we have to break up the lattice, so we've got to put energy into the system to break those bonds that form in the solid state to form those aqueous ions. And finally then, the Gibbs energy of hydration, whether that be for the cation and the anion, is negative. When we dissolve something in aqueous solution, when we dissolve an ion in aqueous solution, energy is released. Now there's a general rule that can be used to predict whether or not these salts are soluble in water. And this is a very general rule. If there is a small cation and a large anion, then we predict solubility. If there is a large cation and a small anion, then we predict solubility. However, ions with similar sizes tend to be insoluble in water. So what we're saying here, if there is a large difference between the ionic radius of the cation and the anion, then we would predict that that salt is soluble in water. If that difference between the ionic radius of the cation and the anion is small, and they are very similar sizes, then we would predict that that salt would be insoluble in water. So if we have a very large difference then in ionic radii, let's say we have a very large anion and a very small cation, why is that salt soluble? Well, in this case, this Gibbs energy of hydration term heavily dominates and is very large and negative. And the reason why that is because the hydration enthalpy of a small ion is very large, i.e. more energy is released when a small ion dissolves in water as opposed to a larger ion, and that's because of the effective nuclear charge being higher with a smaller ion, and therefore there being a stronger attraction with water molecules and much more energy being released when that small ion dissolves in water. And if this Gibbs energy of hydration term dominates, is large and is negative, then it means that the overall Gibbs energy of solvation is also negative, and we predict solubilization of the salt. Now, when these ions have a similar size, if we imagine having two small ions, so a small cation and a small anion, although here the Gibbs energy of hydration are relatively large, because we have very, very small ions here, small cations and small anions, they're able to get very close together. And the attractive forces that hold the lattice together are much stronger. What that means is that this Gibbs lattice energy term dominates. We've got to put more energy into the system to break up the lattice. And if that large Gibbs lattice energy, positive Gibbs lattice energy, dominates, then it means that our overall Gibbs energy of solvation term there is positive, and we predict that the salt is insoluble in water. Similarly then, if we have a system with two large ions, so a large cation and a large anion, so again similar sized ions here, we predict insolubility again because this Gibbs lattice energy term dominates. We know here that our Gibbs energy of hydration terms are going to be much lower relative to a system where we have small cations, so the lattice term tends to dominate here, and we predict insolubility. And there's a schematic there that I've taken from one of the textbooks which sums up all of that information. Going back to the question then, we can relate the ionic radii of all of these species to whether or not the compounds that we speak about in the question will be soluble in water. So lithium fluoride is composed of a small cation and a small anion. Similarly, cesium iodide is composed of a large cation and a large anion. So in each case here, the cation and the anion have a very similar size. And we would predict those salts are insoluble in water. However, lithium iodide and cesium fluoride, well, the first there is composed of a small cation and a large anion. The second is composed of a large cation and a small anion. So big discrepancy there in the ionic radius of the cation and the anion, and we would predict solubility in those two cases. Okay, question 2 from lecture 1 is asking about the enthalpies of hydration for some group 1 metals, and it asks you to suggest an explanation for this trend. And as we progress from sodium through to rubidium, the enthalpy of hydration decreases. Now, we just spoke about this in the last question. We spoke about something related to this. The hydration enthalpy is a measure of the energy released when attractions are set up between ions and water molecules. We know, therefore, that attractions are stronger for smaller ions because smaller ions have a greater effective nuclear charge and therefore a greater magnitude of interaction with water molecules. And therefore the hydration enthalpy is much larger for smaller ions, i.e. more energy is released when small ions are hydrated in solution. And as a consequence, that hydration enthalpy falls as you go down a group in the periodic table. Question 3 from lecture 1 asks you to give an account of what happens when sodium dissolves in liquid ammonia. And what happens is a really odd property of mainly group 1 and some group 2 metals. And you get very, very concentrated solutions of the alkali metal. So what happens is that when you dissolve a block of sodium into liquid ammonia, it splits up into the cation, the solvated cation, and a free solvated electron. And that free solvated electron is stabilized by a cavity formed by the ammonia solvent and hydrogen bonds with hydrogen atoms on the ammonia molecules. And the solutions are a very, very deep blue, and really interestingly they conduct electricity at around about 10 times that of an aqueous sodium chloride solution, and that's all to do with that tiny, tiny freely solvated electron being highly mobile in solution. And as you increase the concentration, as you add more sodium metal to that ammonia solution, the conductivity goes up and it actually shoots up to values which are comparable to that of the pure liquid metal. And you'll remember that this isn't just a bit of quirky chemistry, it's a really odd thing to have a freely solvated electron in solution in chemistry. It's very, very rare, and it's not just a quirky bit of chemistry. That freely solvated electron is a very, very strong reducing agent. And we spoke about how this is used in the Birch reduction, and we also spoke about how this is used in a lot of inorganic synthetic procedures where a very, very strong reducing agent is required. Right, so moving on to some questions from lecture 2. Question 2 from lecture 2, to be precise. The question is the lattice energies of SRO and SRO2 are minus 3,220 and minus 3,037 kilojoules per mole respectively. Show that these values are consistent with estimates obtained using the VBT approach. And some of you have asked me specifically about this question. This appears towards the end of lecture 2 and concerns the volume-based thermodynamic approach. So we can experimentally determine lattice energy, but we can also calculate it theoretically, and the advantage of that, of course, we spoke about this last year actually in SE5014 in the inorganic chemistry component of that module. The major advantage here really is being able to calculate the lattice energy of a crystalline solid allows us to confirm and match up with theoretically derived lattice energies. And one approach to calculating lattice energy uses this volume-based thermodynamic approach, and as you might have guessed, it relates the lattice energy of a crystalline solid to the inverse cube root of the volume. And the equation there is shown. And what I just want to confirm with you guys is that I will always give you this equation in the exam, so this will be in the appendix of the examination. And secondly, I will always give you values for I, alpha, beta, and the volume of the ions that are involved. So I'll show you the kind of information you can expect from a question here. So you'll get the question, but you'll also, as I said, get the values from the equation. So I, alpha, and beta there for 119 and 60 respectively. And you'll notice here that I give you the volume of the ions. So I give you the volume of Sr2+, the volume of O2-, and the volume of O22-. And you can then calculate the lattice energies. So I give you some lattice energies here, some experimentally derived lattice energies, and we can start by calculating the lattice energy of SRO. So we take our equation to calculate delta U, we plug in the numbers, and you'll note I've just added the volume of Sr2+ and VO2- here. Calculate the lattice energy, and the value we get is 3037.76 kilojoules per mole. So that's the calculated lattice energy of SRO. And coincidentally, the theoretically calculated one is exactly the same as that as SRO2, but we'll speak about that in a moment. I can do exactly the same for SRO2, and I can feed in the numbers there to get the lattice energy for SRO2, and the theoretically determined lattice energy there is 2904.24 kilojoules per mole. And if you remember, when we spoke about in this lecture, we always said that the peroxide for group 2 metals is less stable than the monoxide, and that the monoxide will always have a more negative lattice energy than the peroxide. And this we determined was a simple size argument. The fact that that peroxide anion is much larger than the oxide anion, and therefore in the oxide, ions can get much closer together, and the attractive forces holding the crystalline solid together are much stronger, and therefore the lattice energy is more negative, i.e. more energy is released when the solid forms, or you have to put more energy in to break up the lattice. And if we look at our theoretically determined values here, so we calculated the lattice energy for the oxide as minus 3037 kilojoules per mole, and we calculated the lattice energy of the peroxide as minus 2904 kilojoules per mole. Now, they are pretty close to the experimentally determined values that I gave you in the question, but most importantly, that trend is conserved, right? So the fact that the peroxide has a lower lattice energy, if you like, or the oxide has a more negative lattice energy than the peroxide, that trend is conserved, and therefore our volume-based thermodynamic approach here matches well with those experimentally determined values in the question. Now that's the answer to question 2. You'll note then that question 1 is a fairly similar question and asks you to use this volume-based thermodynamic approach. So question 1 from this lecture 2. And all you've got to do there is take the equation that appeared on the previous slide and apply that to calculate the values of the lattice energy for the compounds that are in question 1. And if you want to know where to get values of I, alpha, beta, and the volumes of the ions involved, well, you can simply look those up online, or you can take a look in the Housecroft Inorganic Chemistry textbook, and all of those values are in the appendix, I think appendix 6 of that textbook. But like I said, in the exam I will always give you those values, and I will furnish you with the formula as well. Okay, so question 3 from lecture 2. Suggest explanations for the following observations. The energy released when a mole of crystalline barium oxide is formed from its constituent ions is less than that released when a mole of magnesium oxide forms from its ions. Each compound possesses the NaCl structure. Well, this comes down to the stability then of the group 2 oxides and the fact that their stability decreases as you move down the group. So I show you there 3 lattice energies for magnesium oxide, calcium oxide and strontium oxide, and you'll note that the lattice energy is higher for magnesium oxide than it is for strontium oxide further down the group, i.e. that lattice energy becomes less negative as you move down the group, i.e. less energy is released upon the formation of strontium oxide versus magnesium oxide, or if you think about it from the other direction, you've got to put more energy in to break up magnesium oxide than you have strontium oxide. So that comes down to a size thing. Again, those cations at the top of the group, we've got a consistent anion size here. Oxygen size of the oxide anion doesn't change, the thing that's changing here is the size of the cation. Magnesium, being further up the group than barium, is smaller, and therefore the cations and anions in that system can get closer together. If they can get closer together, then those attractive forces that hold the lattice together are stronger, and in the case of magnesium, more energy is released when it forms from its constituent ions when compared to the barium oxide case, which is a larger cation. Cations and anions further apart in that system, attractive forces holding the lattice together are lower. Okay, now lecture number 2, question 4. For which of the following gas phase species is the VSEPR model in agreement with experimental observations? And there are 3 options there: BECl2, BAF2 and MgF2. So this requires a slight sort of cast your mind back to first year, when we were speaking about VSEPR theory and molecular shape, or at least the first part of the question does. First thing we need to consider is, okay, well, what molecular shape does VSEPR theory predict for these molecules? And for every single one of them, it's linear. So if you need to take a look back at the kind of initial lectures for SE5014 and inorganic chemistry when we spoke about VSEPR theory, but the first thing we need to realise for this question is that VSEPR theory would predict a linear shape for every single one of these molecules. The next thing to consider in this question is that we're talking about gas phase species of these molecules. Remember that we spoke about the structure of group 2 metal halides in the gas phase, and the fact that these were the subject of quite intense theoretical interest. And that's because some of these species are what we call quasi-linear. So just to introduce the notion of quasi-linear again, this is a species for which the calculated energy difference between a linear and a bent structure is less than 4 kilojoules per mole. And when you look at this definition, you arrive at, theoretically, some of the structures for the group 2 metal halides. You can see that some of them are linear, some of them are in this quasi-linear state and are likely to be moving constantly between a linear and a bent shape, and some of them are permanently bent. So particularly those group 2 metal halides of the later elements in group 2, barium and strontium, tend to exhibit this bent or quasi-linear type structure. And there are a couple of theories. There's a lot of debate in the literature as to whether or not these are bent, quasi-linear or linear, but these are the main structures that have been arrived at, and there are 2 possible reasons as to why these molecules adopt these kinds of structures. The first is called inverse polarization, and the second suggests that we may even be seeing some participation of d-atomic orbitals for the calcium, strontium and barium halides. Now, I'm not going to go through these. We went through them in the lectures. Please take a look back if you'd like to in the lectures. The crux of the question here, which of course identify which ones agree with VSEPR theory. If you look at beryllium chloride and magnesium fluoride, we know that VSEPR theory predict a linear shape, and indeed it's been shown that in the gas phase these molecules adopt a linear shape, so they agree with VSEPR theory. The trick with this question was to note that barium fluoride, BAF2, is much further down in group 2, and therefore is likely to adopt, or does adopt, a bent structure in the gas phase, and therefore does not agree with the SEPR theory. So I think the key to this question is remembering that those earlier group 2 metal halides tend to adopt linear structures and therefore agree with the SEPR theory. As you move down the group, especially towards the later group 2 halides, strontium and barium, they tend to form bent or quasi-linear structures in the gas phase. So remember that this is all in the gas phase. Okay, and what I wanted to do then was just to remind you about answering questions regarding boranes, and to remind you of Wade's rules and how we can predict the shape and structure of boranes using Wade's rules. And I'm going to go through a couple of examples from the lectures. This is from lecture 3. This is question 1. I'm going to go through a couple of examples. So rationalise why B6H62- adopts an octahedral cage. And you'll remember then, I'm not going to go into all the detail of how these things bond and other aspects of boranes or their uses. We spoke about some of these things in lectures. I just want to concentrate on Wade's rules and how to answer these questions. And you'll remember then that there are a number of steps in Wade's rules that we can use to predict the structure of a borane cluster. And this is perhaps the most simple, B6H62-. The first thing we've got to do then is to determine the number of BH units. And we assume that each boron atom carries one terminal hydrogen atom, and therefore that each BH unit provides 2 electrons ready for cage bonding. So in B6H62-, we've got 6 BH units. We then count any additional hydrogen atoms that are present, and each additional hydrogen atom provides 1 electron for cage bonding. In B6H62-, there are no additional hydrogen atoms, so we don't have to worry about any more electrons from hydrogen atoms. We've then got to add up the number of electrons that are available for cage bonding and take into account any charge in the system. So here we've got a 2- charge, so we know we've got 2 extra electrons within the cage, and we can use this and sum the number of electrons here to work out the number of electron pairs. So we've got 6 BH units here multiplied by 2 because each BH unit provides 2 electrons, plus 2 electrons when we take into account the additional charge in the system, which brings us to 14 electrons and 7 electron pairs. And we know that the number of electron pairs is equal to n plus 1. And importantly here, n is equal to the number of vertices in the parent deltahedron. So we can determine the parent deltahedron just from knowledge of the number of electron pairs. So we know we've got 7 electron pairs in this system. Therefore, we know we've got 6 vertices in the parent deltahedron. So the parent deltahedron must be an octahedron. We've then got to distribute the BH units throughout the vertices of our parent deltahedron, and each one of those BH units will occupy 1 vertex in the parent deltahedron, in this case an octahedron. And nice and simply with this one, we've got 6 BH units which occupy all of the vertices in the octahedron. And the number of vertices which remain after you've dished out all of the BH units determine the class of the cluster. So in this case, we've got no vertices left once we've distributed all of those BH units, and the class of the cluster is a closo. Now, we can also continue with this. So let's now try and suggest a likely structure for B5H8 minus. Again, we determine the number of BH units. We assume, just with the previous example, that each boron atom carries a terminal hydrogen, and each BH unit provides 2 electrons for cage bonding. Here we've got 5 BH units, but we've now got 3 additional H atoms because we're dealing with B5H8 minus. So when we tot up the number of electrons in the system, we've got 5 multiplied by 2 for our 5 BH units, plus 3 from our extra 3 hydrogen atoms, plus 1 for the minus charge on the molecule. That takes us to 14 electrons, or 7 electron pairs. And we can determine the parent deltahedron. We know that there are 7 electron pairs in the system. Therefore, we know we've got a parent deltahedron with 6 vertices. So the parent deltahedron here is also an octahedron. And if you're asked to suggest the likely structure, then you've got to distribute these BH units. So if we distribute our 5 BH units, we stick those on 5 vertices of the parent octahedron. We've now got 1 vertex left, because each one of those BH units sits on one of the 6 vertices of our octahedron, but there's 1 vertex left. And when there's 1 vertex left, then the cluster class equals nido. And again, sorry, if you're asked to suggest a likely structure, then there is a formal way of doing this. Here, for example, we know we've got a nido cluster, so we've got to remove 1 vertex. And when removing 1 vertex from the parent octahedron, you tend to remove the vertex that has the highest connectivity. Now, usually in a deltahedron, this is going to be one that's a capped structure, right? So you can see which vertex you're going to remove in the octahedral system. And then finally, you distribute those extra hydrogen atoms, and you tend to distribute them into bridging sites, so along an open BB edge, or in an extra terminal site if there are boron atoms of a low connectivity. I will give you this table here. So you're going to be able to see, or a table similar to this, so you'll be able to see the parent deltahedral cages. B, confirm that B6H10 is a nido cluster class. We've got 6 BH units here with 4 additional hydrogen atoms. So that's 6 multiplied by 2 plus 4 electrons to take account of the extra hydrogen atoms. So that's equal to 16 electrons, or 8 electron pairs. And if we've got 8 electron pairs, then we know that there are 7 vertices present in the parent deltahedron. And therefore the parent deltahedron is a pentagonal bipyramid. And those 6 BH units will occupy 6 vertices of the pentagonal bipyramid. And there is 1 vertex left. And if there's 1 vertex left, then we know that it must be a nido structure. So finally then, confirm that B4H10 is an arachno cluster class. Well, we've got 4 BH units with 6 additional hydrogen atoms. That's 4 multiplied by 2 electrons plus 6 electrons to take account of the extra hydrogen atoms. That gives us 14 electrons, or 7 electron pairs. And if there are 7 electron pairs, we know that there are 6 vertices present in the parent deltahedron. The parent deltahedron is therefore an octahedron, and those 4 BH units occupy the 4 vertices of an octahedron. which leave 2 vertices remaining. And if there are 2 vertices remaining, we know that it's an arachno cluster class. So you'll see I'm not really asking you to draw these structures. These structures are quite complicated, and I think it would be a bit unfair to ask you to draw them. But I would like you to be able to confirm, using wage rules, a particular cluster class. Okay, so a few more revision tips. Practice the example questions at the end of each lecture. These are going to be really important. I didn't just put them there for fun. And please do send me your solutions. I will take a look at them, I'll mark them, and I'll give you some feedback on your performance.